Yeah, pleasure to be here. I'm really sorry I missed the morning. I was running my very first subject in a new study since the first one since I got here earlier, so apologies for missing those talks. Let me talk for a moment about why I'm telling you about this work. So the work I'm going to tell you about is trying to find signal in this kind of data, functional brain imaging data, or any kind of data where we're trying to relate neural states to cognitive behavioral states. And as you all know, every such method yields masses and masses of data. So you have to make some kinds of assumptions to figure out which of the thousands of measurements you've taken are the ones that really matter for the kind of thing that you're trying to study. Now, for many years, the approach that people took and became standard in the field is kind of like this one. You make the assumption that the information that you're looking for is localized to some place in the brain. So these are all images that I pulled up when I searched for Nancy Kamwisher and the visual object processing system. And what you can see here is the general idea that there's some part in your ventral temporal lobe that responds when you're looking at a place or a face or an object or a visually presented word and so on. And if things really are organized like this in the brain, it's great because that means we can interpret what a given brain area is doing without having to take into account what the whole rest of the brain is doing. Right? We can look at one area at a time, one voxel at a time. That makes the statistics very simple. But the problem is that more and more people don't really think this is a useful way of thinking about how things are organized, at least not in all of the brain. As we've seen in other talks earlier today, it's very common to think about brains as involving networks that may be distributed across the entire cortex. And if we think in terms of network science, of course, you can try and understand what each node does individually, but really each node is doing whatever it does in cooperation with all of the other nodes that it happens to connect to in the brain, which may or may not be immediate anatomical neighbors, right? There might be some white matter pathway that's connecting otherwise distal areas, and the two neural populations are then cooperating to carry out some process or represent some piece of information. Now, if we think that that's a reasonable hypothesis about how things are laid out in the brain, now image analysis and functional brain imaging is a bit more challenging. So here's a hypothetical model that you might see as a figure in a paper, right? You've got an area that processes a word, an image, an action. Maybe you've got different connecting hubs for different kinds of semantics or what have you. And usually when you read a paper, the network will be organized this way. But when you think about a network, its function is solely determined by the connectivity, which units are sending to and receiving connections from which other units, regardless of how those might be topographically or spatially laid out. So in other words, I can take this nice figure, if I just move those units around but don't change the connectivity, the function that this network carries out is exactly the same. Indeed, if I do it like this, the function is still exactly the same. But now you can see if I'm trying to look kind of in the green-yellow area for what the function is, the two different functions being carried out are sort of interdigitated or interleaved, and it's not going to help me to assume that that local area is all doing the same thing. It doesn't even stop there, because we might imagine that this is Carolyn Patterson's brain and this is Matt Lamonrel's brain, and there's some kind of overall general similarity, but maybe they're not exactly laid out in precisely the same way. So if we imagine there can be some individual differences in exactly where the information gets laid out, then sort of averaging across some area in the brain, same location in every person, might not be the optimal way to find things. And what's more, of course, we're taking thousands of measurements, as I mentioned earlier, so whatever features we're looking for aren't the only things we measure. Everything that we are looking for is going to be buried in a mass of noisy stuff that isn't the particular task or representation or process that we're trying to find. So now you can see that signal discovery, finding the coalitions of neural populations that cooperate to represent information or carry out a process, is pretty hairy. It's like finding a distributed needle in a haystack. So that's why I went down this pathway. Let me tell you about some of the things that we can try to do to solve this kind of decoding problem. The one I'm going to tell you about today is very simple, and you can run it on your own laptop with no specialized computer equipment. And if you want fancier stuff, we could talk offline later. So here's the way I think about things. Imagine we put you in the scanner and we have you, let's say, look at words denoting concrete objects. Maybe you see the word dog. When you see the word dog, you get some pattern of measured, bold response at every voxel in your brain. So maybe 10,000 locations across the cortex or so. You're getting an estimate of that bold change. Each voxel here is represented by a circle, and the color of the circle is kind of telling you, oh, have I increased or decreased my bold relative to rest? Okay. Now I see the word saw, I get some pattern. The word pig, I get some pattern. The word knife, and so on. Rather than now looking at each voxel independently and computing its mean activity in one condition versus the other, another thing we could do would be to look at the whole pattern evoked by any given stimulus and try and learn a model that will predict, for instance, hey, is this thing an animal or not? Okay, that's a very simple kind of, right, rather than is this voxel more active for animals than non-animals, we can take the whole pattern and say, tell me now from this brain picture, was the person looking at an animal or not? Okay? What do I mean by a model? I don't mean anything fancy. I mean regression. You all had regression classes. You probably saw this equation here, right? You have some outcome y hat that's predicted by some intercept, beta 0, plus a bunch of predictor variables. Those are x here. And for each predictor variable, you're estimating a beta coefficient in the regression model, a weight. So x is the data, beta is the set of coefficients that you're learning for those data. And in linear regression, we're just trying to find beta coefficients that come as close to the true data as possible. So for brain decoding, we're going to forget about the intercept. Okay, we're going to say, we're going to try and predict y. Y in this case is the thing an animal or not? It's just a binary outcome variable. We're going to try and predict it from the activation of every single voxel for that stimulus times some beta coefficient, one for each voxel. Okay? Now, in linear regression, we can write this down. Argmin beta just says, find the set of beta coefficients that minimize that quantity in the brackets. Okay? So the quantity here is what's the true label, y, and what's the predicted label, xb. I want to minimize that difference, and in linear regression, we would minimize it by minimizing the squared error. This is all statistics I'm sure you guys have all taken before. In the case of binary prediction, is it an animal or not, we don't want to use that squared error term because we really want the prediction to be bounded at a binary value, let's say +1, -1. So we can just replace that squared error loss with a different function that's suited to a binary classification task. Okay? So the logistic loss is the common one that we use here. And it basically says, oh, if the output is positive, say animal. If it's negative, say non-animal. And it kind of doesn't matter how positive or negative it is. Okay? So this is plain old logistic regression. We can take the entire cortex worth of activation, try and find a beta coefficient for each one to predict the true label of each stimulus. But immediately we have a problem. How many stimuli do you think you can collect in the scanner? Maybe 100? How many predictors do you have in the brain? Maybe 10,000, maybe 30,000? Way, way more predictors than things being predicted, which means that there are infinite number of beta coefficient values that will perfectly fit your training data. You can't just do normal regression because the solution is undefined. So what you have to do is tell your model something else about what you think the solution is like. Rather than just saying, give me beta coefficients that predict well, you have to say, give me beta coefficients that predict well and satisfy some additional constraint. And a very simple constraint is sometimes called the L1 norm or the lasso loss. And it is really just, sorry, I'm trying to find my virtual pointer here. There we go. This guy here, right? So now I'm saying, find me beta coefficients that minimize my prediction error and this second thing. And this second thing is just the sum of the absolute values of the beta coefficients, the model weights that you're trying to learn. Why is it good to minimize that sum? Well, one way of minimizing that sum is to put as many zeros on those coefficients as you possibly can. And if you put a 0 coefficient on a voxel, what does that mean? It means that voxel is not needed to predict well. So when you fit this regression model, it kind of automatically selects a sort of sparse set of features that are doing well at predicting your outcome label. Okay, so this is called the lasso logistic regression. Just to show an example of its use, we applied this to some old data collected by Jared Lewis Peacock. It's a face-place object data set. So 10 different subjects, each one viewed images of 30 faces, 30 places, 30 objects. They're making a pleasantness judgment for each one. And so we have, at every voxel in the brain, an estimate for each of 90 stimuli. And from that data set, individually in each participant, we want to see which neural systems encode whether the image is a face, a place, or an object. These are Nancy Canwisher's templates. If you go to her website and download the face and the place system, this is what you should see. This is our univariate contrast analysis of these data that I'm about to show you. So you can see we get part of her face system pretty well. If we apply the lasso classifier to the whole brain, one thing we can look at and see how well can we do, right? So we fit the model to predict this stuff on 90% of the data. Now we take the 10% we held out and say how well is it doing at predicting face, place, or object. We get 94% classification accuracy. This data is from a multinomial classifier, so literally is it a face, place, or object? So chance is 1 in 3. We get 94% accuracy, so clearly there's real signal in those things. If we look at where those voxels end up being, they end up looking pretty similar to the Canwisherian stuff, right? So we have, red here means elevated activity means face. Blue means elevated activity says not a face, okay? So you can see it's lining up quite well with some of Canwisher's maps, to which, if I were you, I'd say, so what? Why are you making me go through this exercise, Rogers? Here's the thing. Only about 15 to 25 voxels are selected in any single subject when I do things this way. When I say it's a very sparse code, I'm saying it looks like, oh, you've got like a tiny little bit of brain that does faces, places, and objects. Clearly that can't be true. Lasso must be over-sparsifying things. It's kind of picking the smallest set of things that carry information, but not everything that carries information. So that's where we need to do something a little bit more creative. The one I'm going to tell you about now is just a simple twist on the lasso. So the idea is, look, if this was really all the voxels that carry that useful information, then if we take them out of the data set and run the model again, we shouldn't find anything. We should be at chance. If we take them out and run it again and we're not at chance, well, now we found a little bit more of the signal. So we can take those out. In other words, we can iterate. Take our data set and labels, run lasso. Do we do better than chance? If we did, take those voxels out and put them in a bucket. Okay? Now run it again. Are we still better than chance? If yes, take them out, put them in the bucket. Keep going until now your classifier hits chance. Now we kind of say, okay, well, everything that's still in the data set doesn't have any information because our classifier is at chance. But we can take everything we put in the keep bucket, which is now multiple iterations of lasso. That's our feature selection phase. Now we can fit a final model to just those using an L2 regularizer, so something that's going to spread the weights across everything in the bucket. So if we run this iterated approach on the same data set, we're already doing quite well with lasso. Actually have 100% holdout cross-validation error when we do this on this three-way classification with the iterated lasso approach. That was surprising to me. But what's really more interesting is that we're now getting between 200 to 500 voxels per subject selected across that iterated approach. In other words, there's a lot of stuff left after the first round of lasso. And if we look and see where are those guys distributed in the brain, now, all of a sudden, the solution looks very different from the Canwisherian view. So we're still getting kind of the same thing we got with lasso here. We're still getting this bit here, but we're getting all this other stuff distributed throughout different areas of cortex, suggesting that, in fact, that information is not highly localized to a particular area of the brain, but is distributed maybe across a fairly vast cortical network. So I'm not going to go into any of these, but I'll just mention lasso is super easy. There are some other drawbacks to it. We've been exploring kind of more sophisticated regularizer. The SOS lasso is something that prefers solutions that are kind of anatomically clustered in similar ways across people. The growl is a way of trying to decode not just a classifier yes, no, but continuous and multivariate representational spaces. So if you wanted to kind of like look at a principal components analysis of your data set and you think of every stimulus as being a point in some graded space, we can use the growl to try and decode where in that space a given stimulus lies from the pattern of neural activity that it evokes. What are the conclusions? If you want to do whole brain decoding, you have to regularize it somehow. I'm excited about this because it may lead to very different answers to questions about where information is encoded in the brain. And really, if you have a data set lying around, these methods can be applied to any data set that allowed you to estimate kind of the neural response to each of several stimuli. Okay, I'm done. Thank you.